Because there's a weird thing. Because one of the questions that it asks is this strange thing. I just put 0 automatically. Basically, what they give you on your first homework problem is they've got this cube, this conducting cube, all right, sliding along. All right, so basically they've got a metal cube that's moving through a magnetic field, all right, and the magnetic field is perpendicular. And it says, hey, what is the electric field inside the cube? Well, what did you all learn in the first 3 weeks of class? What did I beat into your heads about the electric field inside a conducting surface? It's 0. Not when it's in a magnetic field and moving. Okay? There's going to be an E field there. Why? Because that moving, we'll learn about this in the next chapter, that moving conductor inside that magnetic field, that creates a voltage, right? That creates a force, right? That pushes the charge. So actually, an electron will flow through there. Okay? So actually, an electron will flow through there, and it's like, oh yeah. And so it basically comes down to your first couple problems boil down to this. I'll go ahead and turn on the lights, and then I'll finish the rest of it. But basically, so the E field inside there was not 0, and the magnetic if I have an electric field, how do I find the force? How would I find the force with that? What? F equals ma. Okay, good. All right, well, let's put that up here. But I just have an electric field, and I have a charge. How do I put those two together to find a force?
Add them together.
Add them? Multiply. There we go. All right, there we go. So the charge, so the charge on that electron, Q times E naught, that's going to equal what? The magnetic force, too. That's going to, and boy, you all can see that real good, can't you? Jody, can you see that at all? No. You can see that? Okay. All right. Okay. So, but anyway, this is problem number 1 and 2 kind of combined. And so that equals QVB, and this equals QE naught. So does it matter how big the charge is? What the force is going to be? Makes no difference what the charge is because they cancel. All right, I'll go to the overhead now. But anyway, that's just kind of getting you started for the first couple problems. Remember, problem number 1, and I like I've kind of, I like picking the problems that they already have laid out for you all, because most of them are the ones with the hints and all that kind of stuff, and I don't penalize you for using the hints, so use those hints, and they work. I usually don't get any questions. I'm going to kill myself for the days out of. I usually don't get any. Did y'all notice that I'm ready to bail out of here as soon as we're done with this? All right. We've got one of those colloquiums that I used to entice you guys to go to. Not this partner. No, I'm out of here. Because usually I fall asleep after they say good afternoon, and then they start talking about it. I don't even understand the title of their talk, so I'm sound asleep. But anyway, so I just wanted to kind of get you guys started on what you're going to be doing. I'm just going to use the dock camera today, and I think if I just turn on the projector here, boy, they got this roped up the way I can't use it at all. I don't think I need to log in or anything. We'll see. We'll see what happens. Oh, no, I don't need to. Good. Good, good, good. There we go. There we go. All right. Okay, I think that's not bad. That's not bad. Okay. I think we can rotate this around a little bit more, kind of get it more in the middle there. I can get Sean on camera. Cool. All right, flashing. Okay, there. All right, now we'll put that right there. All right, now here we go. Here's where we left off last time. Was you know now that a moving charge through a magnetic field creates a force, right? Now what we're going to find out about is that an electric current creates a magnetic field. All right? Electric current creates a magnetic field. We didn't do that yet, have we? Have we done that yet? And I'm just going to tell you what these are. Okay? I'm just going to tell you what these are. Then we're going to do about 3 examples, and then it's Miller time. Okay? So, and I'm going to pick examples that are like your homework problems. So I was kind of pleased with the homework. It's not bad. Once you get through the first problem, it's okay. After that, it's not bad. All right, so now here we go. Let's say I've got a current. I've got a wire here. Current's going like this. Let's zoom in. Okay. My voice is cracking, everything else. It's like I'm going through puberty all over again. All right. There. Now, what this does is, this creates, and I forgot to bring my visual aids. But anyway, think of a CD. All right. Here we go. Now, let's have the wire, let's have the current. If I say the current's going in this direction, what is that current doing? This current right here, what's it doing? It's coming out at you, right? This is the tip of the spear coming out at you, all right? And if it's going into the board, it'd look like this. This is in, this is out, okay? So let's just look at this current going out, and I'll show you what now this is going to create a magnetic field. What you do is you put your thumb in the direction of the magnetic field, and you curl your fingers around. That's what the magnetic field looks like. It's circular. So with this coming out, you've got all these magnetic field lines here. And of course, they get more intense as we get closer to the current, but they go this direction. As we get further away, they go like this. Further away, that's the magnetic field. All right? So, if I have a magnetic field going straight up, or if I have a current going straight up like this, here's my current going straight up. I put my thumb on that current and go like this. So that means it's going into the board on this side, and it's coming out of the board on this side, on the plane of the paper. Now then, if I take it all the way around through this wall, do you see that the B field is actually going this way in a straight line? In other words, the B field would be going, if on the other side of that wire, it would be going to the left. And then as I come around, it'll be going to the right here, and then it goes in. In other words, just think of it as like a disc with the wire in the middle of it. And the B field's going all the way around. It's solid all the way around. It gets lighter and it decreases in magnitude as you get further away. But this is what it looks like. Okay? So we can figure out so the B field is going like that. And the formula for that, we will not derive this. You can take Physics 460, then you can derive it, okay? But the B field caused by this wire A, caused by that wire A, is equal to mu naught I over 2 pi times, let's say the distance away. That's the way your book does it. I'm used to putting an R there for the radius, but so if I want to find the B field right here, that would be, the B field would, that one's pointing down at that, that one's for this wire right here. I put my thumb in the direction of the wire which is coming out. That B field is going down right there, and it would be this distance away from it, D, from the wire. Okay, now, we've got a new guy. We've got a new constant here. Yes?
This is probably a really stupid question, but B field means magnetic field, right?
Yes,
Is
sorry.
there any other kind of field that we need to be concerned about?
Well, electric fields, but that's earlier. But B field, sorry. Electric field is a magnetic field. I apologize. Right. B is the magnetic field. Good. All right, now, we've got a new character in town, a new constant. He's right up there, near and dear to our hearts, just like the permittivity of free space. This guy's called the permeability of free space. Okay, so mu naught is a constant, and he's called the permeability of free space. Free space, and he's equal to this. Mu naught is equal to 4 pi times 10 to the negative 7 amps per Tesla amps per meters per amp. That's what he is. He's kind of funny. Tesla meters per amp. What the heck? So he's actually, and what are amperes? That's like Q over T. So he's definitely a time factor type thing. But anyway, he's a constant. 4 pi times 10 to the negative 7. And actually that works out to be something like 1.26 or 1.3 times, if you want to round it big time, 1.3 times 10 to the negative 7. Okay, or 10 to the negative 6. Okay. All right, so that's that one. Okay, so that's finding the B field there, and you've got a couple of your homework problems says, hey, you got a wire, and in fact, one of your homework problems is you got a wire, and it's got this much current. What is the B field so far away from it? We can do that all day long. This is for a long straight wire. Okay. Long straight wire. Long cool woman in a black dress. It's a long straight wire. Okay. Now, in fact, one of your homework problems looks like this. And this is a great little test question too. I don't know if it'll be on there. I always say I come up with about 15 great little test questions. There's no way I could give you 15 questions unless I made it a take home. We won't do that. Anyway, all right. Here we got a wire going like this. And we got a wire going like this. Let's say 2 amps is going through this wire. 2 amps is going through this wire. Yes. There we go. All right. 2 amps through this guy, 2 amps through this guy. All right. Now, let's say this is 0.2 meters away, and this is 0.2 meters away. Okay. What is the B field right there? At this point A. We want to find B at point A. What would that equal? Well, first of all, we figure out what this B field is. Now remember, we got to get the magnitude and direction, all right? Because if I got 2 magnitudes, but they're going in opposite directions, what does that add up to be? 0. What do you think this one's going to be?
0.
Yes, it is. Now, if you don't see why, let's examine why. This wire, you take your thumb, put it in the direction of what you basically cup your hands, okay? Or you make these little cross things. I've got you just got this little eye, and this would be like this, and this is like this, okay? And you just slide this guy around. Just go, oh, okay. Oh, that's going in there. And then if I take this guy and put him out here, what happens? He's coming out. And it's the same amperage, right? So if it's the same amperage, mu I times mu I over 2 pi times the distance away minus mu I over 2 pi times the distance away, that should equal 0.
Oh, you just sum them together?
What's that?
If they were different, you have to sum them together?
Yep. Because the B field, the magnetic field is a vector, and so you just add them like vectors. Okay? All right, now, so that's that one. Now, what if these 2 currents were going in opposite directions? What would it be?
Double.
Yes, it'd be double what it'd ever be for one. Because if now, let's switch the direction. Let's take this guy in there anymore. Let's have him go like this now. All right, so this one's going in. Oh, now we've got to turn it around and come like this. Now what is it doing? It's going in. It's double and it's going into the board. Okay? Good. Good, 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 good. All right, now, let's, yes?
What doubles? 'Cause 0 can't double.
Typo.
So
Okay, let's do the work. All right, here you go. Let's figure out, okay, from wire 1, then B on A caused by wire 1, we'll call this wire 1 and this one wire 2, okay? So we've got wire 1 and wire 2. So the B field at A caused by wire 1 is going to equal mu naught times 2 amps over 2 pi times 0.2. Okay? All right? And that is going into the board. Into board. All right? And then let's look at the B field in A caused by wire 2. B field in A caused by wire 2. Now this one is going to be mu naught times 2 pi A, or times 2A over 2 pi times 0.2, and that's going into the board. Are they both the same thing? That's what I meant by doubling it. And so this way, you just add those two together. BA1 and BA2. Very good. Okay. Good question. Good. All right. And a lot of things can cancel sometimes when you're doing these things. Okay, now then, let's say we've got 2 wires. This is going to get hairy here. All right. So, before I go on, here would be a typical homework type question. Here's I going this way, which equals 2.0 amps. And I going this way. Okay? And this is equal to 1.0 amps. This is 0.4 meters. This is 0.3 meters. This is point A. Find the B field here. This is a classic. This is a classic 220 question. Okay? Now, this is just a point A. This doesn't mean the B field's going in or out here. Okay? We'll have to figure that out. So what would we do? First of all, let's call this one wire 1, the one that's going this way, and call this one wire 2. Wire 1's B field, is it going into or out of the board at that point? Had a 50-50 chance. Okay. All right, let's draw a little, let's do this. Bob, give them a visual aid that you can move around. All right, so here we go. I'm going to draw this. Here's my current, and then this means it's going in, and this means it's coming out. Okay?
Which one means in?
In means is that going in is the next, because you're looking at the back of the arrow going away from you. Okay? And this means out. So for this wire, if I put this thing right here, what's it saying the E field from here on over is doing? It's going in. Okay? And then for this wire, what's it doing? Out. There you go. Make yourself one of these little guys. All right? I've been meaning to tell classes that for 10 semesters. Make yourself one of those little things. Then you won't get confused with this. This is a different right-hand rule. This is the curl rule, basically. Okay? All right, so one's going in. Which one was going in? The current 1. and current 2 is coming out, which one's going to be bigger? Well, it's really kind of hard to tell. Oh, wait, no, this is smaller radius, so it might, I don't know. Well, it'd be hard to tell because this one's further away, but it's got a greater amperage. But they're not multiples of each other, so I think this one's probably still going to be greater. Possibly, because it's twice as much amperage. Yeah, and this isn't twice as far away. So, yeah, the 2 will definitely be greater. Sorry, you were having to listen to me think out loud. That could be confusing. All right, now. So, in other words, so BA, let's just get you guys in practice. I shouldn't try and fly through this. That's not fair. Let's go, would be BA of 1 caused by wire 1 plus BA caused by wire 2. All right? But we know that 1 is going in. He's coming out. So it's however you want to orient this thing. You can decide which one's positive, which one's negative. It'll be up to you. But let's have the out for right now. Let's have the out be positive. So this would look like this. It'd be mu naught, which is 4 pi times 10 to the negative 7 over 1.0 amps times 1.0 amps divided by 2 pi times 0.3 meters. Okay? So notice, sometimes if you go ahead and write it out, you can cheat on your calculator. Look at this. This 4 pi and this 2 pi are going to cancel. That's kind of nice. You don't have to mess with that thing. All right? This will be negative plus 4 pi. What's that? I just decided to make, because it was for the going in, I decided to make the in negative and the out positive. Because they're going in different directions. You can make the in positive and the out negative. Doesn't matter. Just make sure they're going in opposite directions. They're not helping each other out. And then we'll look at something kind of interesting here too. Like this isn't the most fascinating thing you've probably ever seen in your life. Over 0.4 meters. And see, this will, again, these guys will cancel, so it'll be all right. All right, so anyway, that's the way you'd find that B field. Now, let's just for one more time for practice, let's put this guy here. Okay? What's that? What now? 1.0 amps. That's an amps. Yeah, it kind of looks like a 4, doesn't it? Okay. Now then, let's look at B. Let's look at B. All I want to do is I want to know which direction it's going here at B. All right? Which direction is it going? So what we do is, for wire 1, what's it doing? Out. For wire 2, what's it doing? Out. So if it's equidistant from the wire, if it's equidistant for both wires, it's just double whatever the one magnetic field is. So yes, these things are kind of handy. Make yourself one of these, and then you can do your homework problems. All right, now we got to talk about something else. Got to talk about this other thing. Now, if a straight wire causes a magnetic field, if the current's coming out at you, the current's my pin, and it's coming out at you, and the magnetic field's going all the way around it like this, what happens if I take this wire and bend it into a loop? Okay? If I take this wire and bend it into a loop, then I get this. I'm going to try and draw a loop the best I can. And what the heck? Let's just do it this way. I'm just going to draw the loop this way. Okay. Here's the loop. And this is I now. This is I. Okay? Now, the B field that's caused by this, guess what? Is straight. The B field is straight. Okay? And what you do is, it's just like grabbing a bicycle tire. Okay, so you grab the bicycle tire, put your thumb in the direction of the loop, and then which way your finger's pointing? They're pointing straight. So this one right here at this point, the B field is coming straight out at you. All right? It's coming straight out at you. And that one, so right here, dead center, it's coming, nope. It's coming out, the B field here at point A. So the B field at point A caused by I, caused by that wire, is equal to mu naught again times I over 2 times the radius of the wire, times the radius of your thing, of your loop, where this is R.
Can you draw the field?
Can I draw the magnetic field? Yeah, it's coming straight out at you. There it is. It's a point coming straight.
On the circle.
Can I draw the magnetic field?
You said it's going to be lines.
Oh, okay, good. All right, this is what, okay, here's the magnetic field. It's going to be all these lines inside here. It's going to look like this.
Or those outs are in.
They're coming straight out at you. And the closer we get to the wire, now for the most part, we say that they're pretty much uniform inside here. It gets a little bit hairy. In fact, that's what you do in Physics 460 is you compute, well, what is the B field this close to the center? Who cares? All right? For the most part, we're going to just deal with the thing being at the center, okay? All right. No, there's no 2 pi. There's no 2 pi. Yeah. It gets canceled out in the calculation when you actually derive this thing. Good catch, though. Good catch. All right. Mooey's still awake. Good.
Field on the outside of the loop.
Oh, yes, there is.
So they're out.
Oh. Wait, is there a magnetic field?
No.
Yes. And it's going into the board. Because what do you do again? You grab your bicycle tire and you curl your hand all the way around. All right? So this actually it's going straight when it's inside the wire. It's coming straight out at you, but it's actually curving around. So actually what the magnetic field kind of looks like, oh boy, this is going to be kind of hard, is it's coming out here and kind of looping around like this. And then coming back through and coming out, looping back around. Okay? In all these places. Okay? So you got this B field, and it would be coming out here and then kind of going like this. Coming out here and then going like this. Okay? All right, so it's wrapped around that wire. Very good. That's good. Good question. Because it's hard to visualize this stuff. It's hard to visualize, especially on a rainy Friday afternoon. But there you go. Now, I noticed your book doesn't mess with this one too much. Doesn't mess with this one too much. But this leads us to a nice little thing on what we call a solenoid. Okay? And you have a cool little solenoid problem on your homework. And then we'll do one more type of problem. Most of your homework deals with those long straight wires, okay? With currents going through the long straight wire. All right, so now, let's take a look at a solenoid. And basically what a solenoid is, and I'm going to put this in parentheses next to it so that you will recognize it when we get to it next chapter. A solenoid is used as an inductor. Okay? And inductors are kind of cool things because, like capacitors, instead of storing an E field, though, like capacitors do, inductors will store a B field. Okay? And magnetic field. Right. Okay, so it's always that magnetic field. Okay? And the electric field, yeah, it makes more sense. If it was the M field, I wouldn't have to say it. But it's the B field. Why, I don't know. But anyway, so solenoid stores it in an inductor, and it's also what we use, the classic solenoid that you all have probably seen before is, well, you've done it before. Did you ever wrap wire around a nail? And then attach that nail to a 9-volt battery? Oh, really? Wow, you created quite a magnetic field that started. Oh, okay. Right. Okay, good. Well, anyway, you can do that. But one of the things that you'll see, now a solenoid looks like this. A solenoid looks like this. think of a solenoid as a tennis ball can, okay, with all these wires wrapped around it. Thousands and thousands and thousands of wires wrapped around it, okay? All right? And they call that wrapping of wires turns, all right? Where it's got N turns, capital N turns. But actually we use small n, which we will say is turns per meter when we use the solenoid formula, okay? So this is what a solenoid looks like. Now, let's say all these currents are going this way as we wrap it around. So the current is going this way. It's going down as you guys see it. So basically I've got the current coming down. So when I grab this solenoid, think of it like a slinky. Okay, anyway, I forgot my slinky. But anyway, if you grab the slinky with your thumb going down, can you see how the currents are going down? Which way is that magnetic field going? No. It curls. Remember, this is the curling thing? Yeah, you should have a huge magnetic field coming out this way. So you got the magnetic field coming out here. You got the B field coming out of here, okay? And then it loops around just like a bar magnet. So you got the B field coming back in here, B field coming back in there. So you got this huge B field that's going this way through this thing. And so now I've built a bar magnet basically inside this thing. And you can build it out of air, which is really cool. Yeah. there will be a magnetic field in there, okay? And this is what they have in your computers, because with the frequency that they store that in, when they turn this off, they use materials that will hold the B field, and so that's the way you store all that data. Then you fire it back up again, and it gets into the semiconductor technology and all that, but you fire that up again to retrieve the data. But the most common thing that you've seen a solenoid for is junkyards. That big magnet in a junkyard, it's a huge solenoid. It's got all these wires wrapped around the outside of it. They fire it up, they turn it on, and then that iron core inside that thing that's picking up the cars, okay, it's got a huge magnet, it's got a bunch of current, multi-hundred amps. I don't know if that's what it is, but a bunch of amps flowing through this thing, okay? You get 100 amps flowing through this thing, it creates a B field, comes down, and that iron core picks up your car, and then what happens as soon as he turns it off? It stops, and so you can drop it. Okay, that's the way you can turn magnets on and off, is you make an electromagnet, and so as soon as you stop the power to it, it shuts off, and boom, you can drop the car. Okay, all right, so that's solenoid. Now, your solenoid equation looks like this for the B field, for the magnetic field. For a solenoid is equal to mu naught I times N. I should have made it mu naught N times I, but I was thinking that's it. That's the magnetic field that's inside a solenoid. Okay? So, let's look at one of your homework problems for the solenoid. It says this. This is the way it reads. But before we get into that, all right, let's say I've got one solenoid that looks like this. Okay? It's the amperage is going down. And let's say I've got let's say 1,000 turns per centimeter. Well, I need to get that's big N, is 1,000 turns per centimeter. I need to get that little n. I need to, how many turns per meter will it have then? What do I need to do to this 1,000 turns per centimeter?
Convert it.
Yep, to what? How should I do that? Multiply by 100, exactly. So we multiply this by 100. So that's 100,000 turns per meter. So n, my little n, equals 100,000. And let's say this I is 15 or 10 amps. I on the inside for the inside, I haven't told you what the outside is yet, is 10 amps. Now, let's say I put a sleeve on this thing, because we do this thing to adjust the magnetic field in circuitry. So that I on the inside was what? 10 amps. Now, I put a sleeve on it that's got the current on the sleeve that I'm going to slide over this thing that looks just like I'm going to put another solenoid over the top of this one. Slide it over the top of it. Okay? But this one, the current is actually going up like this. Okay? It's going up. So now when I draw this current for this solenoid, it's going to be going which way? Which way is its magnetic field going to be going? It'll be going what? Yeah, it'll be coming out this way. Okay? Because what you do is you look at the direction of,
How can we put our little symbol on that thing?
you can't. This is for current. That symbol only works for a long straight wire. Okay?
So how do you turn your hand to be like the flat one? This way or this way?
Okay, what you do is you just think of us. All right, try and picture in your mind. Oh, let me do it this way. Hold on 1 minute. Hold on 1 minute. Here's what we'll do. I got an idea. Okay, 4.
Are you looking at your fingers or your thumb whenever you're doing this?
Look at them both. Okay? In other words, your thumb is always the current. Put your thumb along the direction of the current. But here's what we'll do. I'm not going to log into the thing yet.
You always have to use your right hand.
Yes. Let's go to here. Pull this up. Where's Faraday's lab? That's what I want. There we go.
Run.
Here we go. All right, let me slow this way down. There we go. Now then, which way is this current flowing? Which way is the current flowing on this thing? Okay, you put your thumb along the current, okay? Put the thumb along the current. Now remember, and then which way is the, oh shoot, this guy, that's right. We use, the way we solve our problems in our book is we just use the standard notation where we pretend it's protons that are flowing, okay? We pretend protons are flowing. What's this one doing? It's doing the real deal. And electrons are flowing, all right? So, but it'll still work out. It'll still be okay because the polarity is what matters. The polarity is what matters. In other words, if the north end is, if I say this is the north end, because what he's doing is he's doing just the opposite of what I've been telling you. Because the red line tells you what? The direction of the magnetic field, right? Okay? But as long as the north and south, as long as I say north and south are like this, and I keep it that way, then we're good. Okay? So basically what we're doing is pretend, I'm just going to tell you, don't even pretend. I'm just going to tell you for our purposes and for the standard rule, we can thank Ben Franklin for this. For the standard rule is if the current's flowing up, we're going to say these white guys, the white arrows is the direction of the field. Okay? The white arrows is the direction of the field. So now look what happens.
So is that outer end?
It's going through the center of the thing. Going through the center. All right, so you got, here's your coil, right? Grab your thumb like this, and the magnetic field's going in like that. All right, so right here. Magnetic field's coming in. Current's going up. Now, look what happens when we change it. We change the we change the polarity. Now, it's going down. Now, which way is it going?
Down.
No. Which way are these arrows going? The white arrows.
Right.
To the right
To the right. To the right. And now, let's change it one more
What
time.
I'm supposed to be looking for. I think that's
your
where I'm
glasses.
confused. We're not looking at the blue dots?
The blue dots are what?
The current.
Yes.
What are you asking for?
I'm asking for the direction of the magnetic field. Now, which way is the magnetic field going? To the left. Right? Let's change the polarity one more time. And which way should it be going? To the right. To the front. To the front. I feel a whoop coming on. To the left. All right. Yeah. You guys are too young to remember the 69 boys. I know you are. Way too young to remember the 69 boys. But anyway.
I think I got it now.
Okay, good. All right. Now, y'all should thank Sarah for taking a round for you all, okay? In other words, because I know a lot of others were sitting here going, I'm glad she's asking this because I don't see this shit either. So that was good. That was good. All right, now, so let's call it a day. All right, let's call it a day, and we'll finish. I was trying to blow through magnetism in a week. You can't do it. You can't do it. So we'll finish it on Monday.